All right, so remember that you can access your ebook from Canvas. So if you do need to look over something for the homework, even though the homework kind of has that built-in Learn tool, so it does pull up the stuff from the ebook. But under Bookshelf, you should have a copy of the ebook. And if you click on it, it wants you to register something. It's just a Vital Source account. It's no big deal. It's pretty easy to register. You can also use the Vital Source Bookshelf app on your phone, and you can, once you've accessed it through Canvas, you can download the book to your phone if you needed that. Like if you think maybe you'll go somewhere that doesn't have internet where you need your book, or you don't want to have to wait for it to load, you can do that. It's called the Bookshelf, Vital Source Bookshelf app. We are in Chapter 3, Section 4, and we're going to look at some histograms and other type of graphical displays. So a histogram, and you can see one if you look at your PowerPoint on 3.4. In the bottom left-hand corner, you can see a good example. Your book says a histogram is a graphical representation of a frequency or relative frequency distribution. The horizontal scale corresponds to classes of quantitative data values, and the vertical scale corresponds to the frequency or relative frequency of each class. So pretty straightforward. The one that you're looking at, if you want to see it in color, the handout that I gave was not in color, of course. Looks like that. So you have your classes down here. Notice that, what do these numbers look like with the 0.5 and the 0.5 and all that? Those look like the boundaries between each class. Okay? And so you see each class is represented, and then the frequency, depending on how many are in that class, is represented by the vertical scale. So it says, if you split the histogram of a distribution down the center, the left and right sides of the histogram are approximately mirror images of one another. All right, so if you do that, and they are mirror images of one another, then the distribution is said to be symmetric. So this one here, if I split it right down the middle, like that, I don't have exactly the same thing on the left side and right side, but it's close. All right, and so if they're approximately the same, then the distribution is symmetric. A skewed distribution, if we say that a distribution is skewed, of course it's not going to look like that. All right, it's going to look different. But your book says a skewed distribution is a non-symmetric distribution that extends more to one side than the other. The distribution is said to be skewed to the right or positively skewed if the tail of the right, if the tail to the right of the peak of the distribution is longer than the tail to the left of the peak distribution. So that's kind of confusing. So we can have something skewed to the right or skewed to the left. That's what those two slides are talking about, skewed to the right or skewed to the left. Let me show you a picture of, in general, the shape that would be made for each. You might want to, this isn't in your PowerPoint, so you might want to copy these down. So you can see that it's kind of the opposite of what your brain would think. It would be, it's skewed to the right if you have more data on the left. and it's skewed to the left if you have more data on the right. So, or the tail, they call this the tail. Kind of looks like a tail, how it comes together here. The tail is over to the right. And here it's skewed to the left if the tail will be over to the left. And that's if you were to, you say, well, I don't see any rectangles there. There'd be rectangles in here. But if you were to draw kind of like something like this that touched the tip of those, and then touch the tip of those. All right, so that would be symmetric, the way that it looks there, that I just drew with that red line. Then, if more data items were to the left, it would be skewed to the right. And if more data items are to the right, it's skewed to the left. Okay. All right. This shape right here that I made, the one that I drew here, where it was symmetric, that's called bell-shaped. So, if you've had any type of statistics that goes into looking at probabilities, then you've probably heard bell-shaped or a normal distribution or something like that. But not trying to throw too much on you at once. But if it kind of looks like, like it's the same on both sides, that's bell-shaped or normally distributed. I don't think your book even says that yet, so don't worry about it. But it is important. Another way to present data is by a stem and leaf plot. All right, has anyone ever seen a stem and leaf plot? Maybe in a math class. I don't even know where it would be presented. I guess around looking, if you were doing some statistics in a maybe a math class in high school, you would see something like that. A stem and leaf plot is really just a way to present data in a compact form. Your book says the stem and leaf plot is a graph representing quantitative data that separates each data value into two parts, the stem and the leaf. All right, so let me show you what we're talking about. And for small sets of data, it really doesn't shorten or it doesn't really present the data in a compact form. But for large sets of data, it would. So let's say that this was our data set right here. I know this is a small data set. We'll look at one that's larger. But the way that you would make this into a stem and leaf plot or stem and leaf form would be to separate the first value and the second value into a table like this. Again, for a small amount of data items, it wouldn't make sense to make a stem and leaf plot really. But this line right here, this row, means 97. And this row means 99. This row means 108. 110, 111. And so you can see it doesn't make a lot of sense to present a small amount of data that way. If you look at the table that's in your PowerPoint, let's see. They are making a stem and leaf plot to compare the annual home run prediction of Babe Ruth and Barry Bonds per season. So we could take, and this is all in your PowerPoint. I'm just going to copy it up here so you can see it in color. So we could take a big set of data like this. All right. Where we have the home run predictions for Barry Bonds and Babe Ruth. Is this home runs? Let's see. I'm sorry. This says home run production Babe Ruth and Barry Bonds hit per season. All right. And the stem and leaf plot could take all of that data, all the different hits, all right, and put it in one table like this. So that you have, you know, like a first number and a last number. That's what I'm guessing. There's Barry Bonds. There's Ruth. I'm guessing that this is the stem for both of those, and then this is the leaf. I'm trying to see how it's organized. It doesn't. It says key 06. 1 equals 60 home runs for Ruth, 61 home runs for Bonds. Because that wouldn't make sense. I guess this is the that's kind of strange. I guess comparing the different years. So they got a little creative there with their dot plot, I guess. I'm not dot plot, their stem and leaf plot. Another way that this could be used would be like, I could organize grades this way, I guess. I don't know why I would, because I'd rather see them all. But if I wanted to write the numbers down for grades, and I wrote maybe for one test grade, or maybe this was 4 test grades for somebody, where this would be like the stem, and this would be the leaf. This would actually mean they made a 99 on one test, they made an 89 on one test, they made a 79 on one test, and they made a 59 on one test. Okay. So it's just different ways to organize data. Nothing special. If it confuses you, I can help you with any of the homework. It's not really that big of a deal. It's just one way to present data. Another way, it says an ordered array. An ordered array is a listing of all the data in either increasing or decreasing magnitude. All right, it's a listing of all the data in either increasing or decreasing magnitude. All right, so that just means we take all the data and then we order it, basically. And most of the time, I would say in here, we're going to order things least to greatest. Here's an example. And I believe this example is, yes, this example is in your PowerPoint on this section. So if you had a big set of data like this, age of employees. Well, before we can start doing things, some of the things that we want to do with this data, it has to be ordered, okay? And so we would want to order it, then we could do other statistical stuff to it. That's an ordered array. So another type of way to present data is by using a dot plot. All right, so a dot plot is a graph where each data value is plotted as a point above a horizontal axis. All right, so let's see what we can do. Let me see if I can draw a straight line first. All right. All right. So everybody participate, make this more fun. How many people were born in January? Raise your hand. 2. All right. How many people were born in February? 1. Just 1. What about March? 1. Got a lot. Let's have a lot coming. What about April? Not May. 1, 2, 3. June. Only 1. July. What? That's like almost statistically impossible. August. 2, 3, 4, 5, 6. 3, 4, 5, 6. September. October. Wow. November. 2, 4. December. 1, 2. All right. So I know I didn't put dots. I put X's. It really, it's a dot plot, but I've seen it with X's. I've seen it with different symbols or whatever. But that's a dot plot. All right. So it's pretty easy to understand. If you look at your PowerPoint at the bottom, they show you a set of data, and then they have that set of data plotted. So you only have this one axis, this one horizontal axis, and then you put a dot or a point or whatever above each one of those. Dot plots. A time series plot. Let's see, still in 3.4. I know the PowerPoint may have ended. A time series plot would just be a plot done like over time. Here's an example of the type of data that we would need. Here is the U.S. Census data. So this is the population of the United States starting back in 1790. Now, I'm always skeptical of data that doesn't end in 0. Okay, and that's one of the things I always look for when people try to get so precise with large numbers. I mean, I really doubt any of these are exact numbers. Maybe some of the smaller ones, even though, think about it, when you start counting in the millions, how are you going to keep up with everybody? Okay. We have a census coming up in 2020. Very important census. Most of you are getting to the age now. In 2020, you may You may already have your own apartment or house, but you may have your own apartment then, your own house then. When you see that packet come around, don't just let it lay there, Fill it out, send it in. It is very important. I saw one of the hot topics right now is that our president wants to put a question on the census that says, are you a U.S. citizen? And a lot of people are against that, putting that question on there. I say that it will mean that we won't get as many replies because there are lots of people that are in our country that aren't U.S. citizens, and so they will think that if they fill that out, maybe they'll be deported. What do y'all think about that? Hot topic. Y'all think that it would be okay to have a question, are you a U.S. citizen on the census? Well, I mean, the data is used for all kinds of things. One of the things that it's used for is to assign electoral college votes in the different states. So, let's say there's an estimated 2.75 million illegal, or you can say there's two ways to say it. I don't want to offend anybody. You can say illegal immigrants or undocumented immigrants. You will notice that most Republicans will say illegal immigrants and most Democrats will say undocumented immigrants. It means the same thing as far as I know. I may be wrong. I'm not going to try to sway you one way or another. But, okay, so California has approximately 2.75 million undocumented immigrants. So, do you think that they should be able to count those people to base the number of electoral college votes that California gets? I mean, that's not the only reason we send out the census, but that's one of the reasons. What do y'all think? You're not wanting to talk today. I mean, in the South, a lot of people, are going to lean one way over the other. I don't know. I don't know what the correct answer is. What do I think? Honestly, if you want to know my opinion, I hope I won't get fired over it, would be that I believe that we should have stricter immigration laws as far as who's here, but I think there should be an easier route for people to become citizens of our nation. I think that if people want to become citizens of our nation, it shouldn't take as many years as it does, and it shouldn't take as much money as it does. If you want to become a citizen, why not? I mean, now, do they need to be checked, background checked, monitored to make sure they're a good person to begin with? Yeah, probably so. But I think there should be some easier way to become a citizen. That's just my opinion. Everybody has their own opinion. But the census. So in 2020, I mean, there's probably a function out there that we could just plug in 2020 and estimate how many people are going to be in the United States in 2020. Looks like it'd probably be about 330, 350 million, somewhere around that. But again, if you get that packet, fill it out, send it in. That's what it's there for. It's there to give information to the country so that they'll be able to make decisions like that. Anyway, I usually don't bring up controversial topics like that, but that's just the year we're living in right now. That's a big deal, the census. So we could take that census though, and we could make a graph on the population over time, a time series graph. So let me show you what it would look like, and we could plot points. We could even make it a line graph if we wanted to. So if we just plotted points, we could make an x-axis and a y-axis, maybe an x-axis for the years and a y-axis with the numbers, and then we could plot the points. And there we go. We draw a line through that, then it's a line graph, right? Kind of like we're used to doing in algebra. I mean, you can see that that's fairly exponential as well. I mean, it kind of follows a pretty good curve there. You can see a dip here. like not as many people here. What do you think happened there? World War II? Probably one of the reasons why. All right. So let's look at this map. Here's a map called a geospatial graph, or this is a type of geospatial graph. And you won't have to know this for your test. It's kind of interesting. It's a geospatial graph called a choropleth map. And it uses a map, a geological map, and usually we have data and we shade the map different ways. So here's a pretty interesting one. This was in 2016. Where were you in 2016? Think about it. If you were in the United States, which state were you in? All right, maybe Mississippi, maybe not. But you can see here, this is a country obesity population. And it's shaded differently in different regions. All right, and so you can see now, does that mean that there are more obese people in certain places than others? Yes. But does that mean that maybe not per area of region, like per capita, it may not be the same. You can see Mississippi, though, we've got some darker shades in there, some little spots. Where's Colin? It's about right there. Look how dark that spot is. No, I'm just kidding. But yeah, it's probably like, so like in this little spot right here, there's probably more people than live in the state of Mississippi. Okay? It's just that ours is spread out. So we don't have a dark blue region in one place other than these little specks right here. But percentage-wise, yeah. I think if you put all of us together, though, in Mississippi, we'd probably create a new color down here. But just because that's we don't know how good we have it. All right. So that was a good question. If you normalize the obesity, that would mean like to spread it out according and make it like a percentage rather than the number of people, like the percentage per unit of area of land. That's what was done in this next map. You can see that it looks different. Well, you may have more people over here that are obese overall. The percentage-wise, you can see it's more. Yeah, more over here. I don't know. I wonder who's living up here in Alaska. I need to go eat there. They must have some good food. All right. So that was 3.4. Three 3.5 is on analyzing graphs. Basically, like about the same stuff we've been covering this entire time, looking at graphs and being able to read what's coming off the graphs. It is important, though, that you always be cautious about any data that you look at, especially graphs, because how misleading is that? If you were to show this graph to somebody and they didn't have a lot of knowledge about what this graph is showing and the population in different areas, if you thought the population was the same across the United States, then you would say, man, these people over here are really, really obese. And these people, you know, down here, they're not obese at all. But in actuality, you know, you may see that it's different percentage-wise. So it's important that look at the graphs, understand what the graphs mean, understand who's providing the data. You know, I told you about the study that was made on chocolate that was backed by Hershey, right? That told you that chocolate had a positive effect over, you know, over long term. So it's very important that you see who's putting forth this data. When was the data taken? The year. If somebody were to put something in a magazine that was in 1940, that wouldn't be too applicable today. So make sure that everything is being represented appropriately. It's important that you, of course, label your graph correctly. Make sure that your graph is appropriate for the data that is being discussed. I've already showed you a graph. I showed you last class meeting a graph where if we change the scale, remember it looked like that one lady was making 3 times as much as the other lady? If you change the vertical axis or you change the horizontal axis, that can change the entire way that the graph presents the data. So it's important that you're careful whenever you label your axis, and you know, always try to be truthful. Or when you're reading statistics or reading graphs and bar graphs from magazines and newspapers, they're everywhere. If you're reading it, make sure that you are careful to the details in the small print. All right, let's see. Let me show you another example of a misleading graph. This is a misleading pictograph. Know what a pictograph is? It's like a graph that has usually little symbols or pictures on it to represent people or items. All right, top 5 forested countries in 2015. This says forest area in millions of square kilometers, and here's the country. So it says this graph shows a potentially misleading pictograph of the top 5 countries ranked in order by the amount of forest area they contain. The bars in this bar chart are represented by trees. Note how as the amount of forest area increases, the trees expand with regard to width and height, thus giving the illusion that the amount of increase is much larger than it is in reality. Okay, so this is the incorrect pictograph because it's expanding this way, which really doesn't do that much. It just visually it looks different, but it's also extending up as you go from country to country. So it's making the trees look a lot larger. Like this one right here, you could probably fit like, I don't know, 10 of these in here if you squeezed them in real tight. But the actual pictograph should look like this. You know, you keep the width the same all the way across. The only thing that increases would be the height that would go with the number over here. Okay, so that's just one way that data can be misleading.